Good afternoon, everybody. Today's topic is image processing using QGIS. I am going to show you a demonstration on how to use the QGIS software to perform image processing. My name is Prasun Gupta. I am with the Indian Institute of Remote Sensing, and the handout and the data that I am going to use can be downloaded from this link. That is https://bit.ly/image-processing-QGIS. So if you just type this in your internet browser, in the address bar, it should take you to a Google Drive where you can download the PDF, the handout, as well as the data. Okay, so the PDF that I'm going to use has step-by-step instructions of what I'm going to do in QGIS, along with screenshots and steps. So it should be easy for you to follow. And the data that I'm going to use has been downloaded from the Bhuvan portal of ISRO. So Bhuvan is the geoportal of ISRO, and there is a section called Open Data Archive where you can go and download different data sets over the Indian region. So for example, I have downloaded this data, the ResourceSat-1/2 satellite, the List 3 sensor. So you can select which area you are in over the country and download the specific tile. So one such tile I have downloaded and I have shared with you. Once you download from the shared folder, you will have a PDF file and a zip file containing the data. Let us extract this. In this folder, you will see that there are 4 images, 4 GeoTIFF files. These are geo-referenced satellite images from the List 3 sensor. That is why the name L3. This is over the Dehradun region over India, in India, abbreviated as DDN, of April 2019. The List 3 sensor captures the data in 4 bands, namely band 2, 3, 4, and 5. Except the blue band, this is the band 2 refers to the green, band 3 refers to the red, band 4 refers to NIR, that is near infrared, and band 5 refers to the shortwave infrared or SWIR. This information you can also find on different websites, such as this one, which talks about ResourceSat-2A satellites. And here you should get information about List 3 sensors and AWIF sensors and all that, which are on board the ResourceSat-1 and 2 satellites. So primarily List 3 has 4, captures data in 4 bands. And we are going to see how we can process these images, these satellite images, in QGIS. So what is QGIS? First, QGIS is an open source GIS software. It is a very powerful and very popular GIS software. It is free of cost. You can all go to this website, qgis.org. That is qgis.org, and click on download now and download the most recent version, which is this one, the standalone installer with the latest release. You can download it in your systems and install it. Currently, I believe this is about 1 GB file, and doesn't require any key or any anything else apart from the file itself to be installed. And it works on all known operating systems. So if you are a Windows user or a Linux user or a Mac user, you should be able to install it. There are separate instructions given here for Mac, Linux users. So for Windows users, all you have to do is just download this and just follow the normal installation procedure and install it on your system. Once this software is installed, on your start menu, you should see several options come up like GRASS, OSGeo, QGIS desktop, QGIS desktop with GRASS, Qt Designer, Saga, and so on. So actually, QGIS bundles several other third-party softwares like GRASS, Saga, Qt along with it. And we are going to use some of these third-party softwares to do advanced image processing using QGIS. So once it is installed, you need to start the version which says QGIS desktop with GRASS, because we are going to use functionalities from the GRASS software also. So you need to start the software which is labeled as QGIS desktop with GRASS. Once you start QGIS, you should see something like this, not exactly like this. You will see some more options on news and things like that come up. You can just click on this white button here on top which says new project. If you take your mouse on it and leave it for some time, and the rest of the things will go away. Let me first tell you about the software, the interface, and then we will start by adding images and then doing some processing on that. So this is the menu bar. You see project, edit, view, layer, settings, and so on. These are different menu options. Then there are some icons like saving a project, opening a new project, opening an existing project. These are your pan tools. The hand icon is used to move the map around. Then there is the zoom, the magnifying glass, the zoom out, the zoom to full extent, and so on. Then there are some utilities like calculating area, calculating statistics, and so on. Then the next toolbar, which is the data source manager toolbar, we are going to use this toolbar several times to add data. So the first icon, that is open data source manager, if you click on it, you will see a box comes up. And this box helps you add vector data, raster data, text data if you have, connect to different databases like Postgres, Oracle, and so on. You can also connect to different web map services, WMS, and so on. So this is an open source software which allows you to connect to or add data from several sources. Okay. Now, so these are the different toolbars. This is the menu bar. On the left side, you are seeing on the top left, this is the browser panel. Here you can directly go to your folders and add data from there. Or you can use the data source manager toolbar tool to add data. Or the most simplest and easiest way that I find is simply dragging and dropping the data. So if I want to open this file, I can simply with my left mouse, left click of the mouse button, I can drag this file and drop it in QGIS. and it should open in the map display panel. This is called the map display panel. This is where your maps will get added. This is called the layers panel. So all the layers will get listed. You can have multiple layers. So for example, I added the band 2 image. Let me add the band 3. And let me also add the band 4. So now I have 4 bands. I can individually turn each of them off or on. And also I can rearrange them. For example, I want the band 3 to be displayed on top of band 2. I can rearrange these layers. They are just like the term layers. They are on top of each other, one top of each other. So they can be rearranged as you wish. On the right-hand side, you are seeing right now what you're seeing is the processing toolbox. This is where all the analysis tools are there. Raster vector processing, Saga, GRASS, Jadal, all these tools are available in the processing toolbox. And then the other most frequently used thing will be the layer styling panel. This is where we will style the data set, that is change or enhance its appearance to help you interpret features on the satellite image. Okay, so I don't need the browser panel. I just need the layers panel, and I need the layer styling panel and the processing toolbox for today's demonstration. If you're not seeing any one of these panels, that is the layers panel or the layer styling or processing toolbox, all you need to do is click on this view menu here and go to panels. And here you need to check these 3 options: layer styling, layers, and processing toolbox panel. There are several other panels which we will not be using today. And you will see over time that these are the 3 most important panels that you require. So right now what I am seeing is, let's say, the band 2, which is the data in the green band of the list 3 sensor. Now the list 3 sensor is 23 meters. The data provided freely by the Bhuvan platform is in the EPSG 4326 projection system. Now, what is EPSG 4326? EPSG codes are unique codes that are given to each and every projection system known. So if you're talking about geographic lat-long in the WGS 84 datum, then the code given is 4326, and that is most common data available on the internet. If you're looking for data of your specific country or specific UTM zone, then you would have a code something like 326, then followed by the UTM zone number. For example, Dehradun or India lies between 7 different UTM zones from 42 up to 49, I think. So this data that I have downloaded has 1,151 rows, 1,151 columns. This is unsigned integer 16. This is basically a integer data set. It is a GeoTIFF file, and this is the location where it is stored and so on. So all this information, the pixel size, so this is in degree decimal. If you convert it to meters, you will get somewhere around 23, 24 meters. How do you see all this information? Just you have to right click using your mouse on the name of the layer, and you can go to the last option, which is properties. In properties, you have again several different options. On the left, you see information, source, symbology, transparency, and so on. The first option, that is information, is where you will get a lot of information about the the satellite image. Okay, so now if I want, I am zooming in and zooming out with the scroll button of my mouse. So if I scroll up, you see I am scrolling in. If I scroll down, I am scrolling out of the image. Okay. You can also use this magnifying glass and drag the area that you are interested in to view it. Or you could use the zoom out button and click on the screen to zoom out of that area. If you want to see the full image again, just right click on the layer name and click on the first option which says zoom to layer. Okay. So till now I've just shown you what QGIS is, how you can add raster images, satellite images, and how you can navigate through your images. Okay. First thing let us do is save the project. Now, several times you will be adding a lot of layers, big layers, having large dimensions, several number of layers, or you will be doing advanced processing tasks. And depending on how fast or what resources are there, what CPU and what RAM, the system will automatically either get slow or it may hang. So it is a good practice to keep saving your project. So in case by mistake the system gets switched off or get crashed, you can still recover all the data, all the things that you have done. So to save the project, all you have to do is click on project, click on save as, and take any place. So right now I'm working on a folder inside my D drive. And let me save it as my project. So what it does is it creates a very small file. So right now you're seeing my D drive data folder. Here you see it creates a very small file, a 4 KB file, which stores all the information about what layers are added, what is the symbology, what is the zoom level, and different other things. Now, you must have studied a lot about satellite images, about pixel values, radiance, surface reflectance, so many different terms. So let us see what the pixels are composed of. These are composed of nothing but numbers. So what you see here as a dark pixel or a dark pixel or a bright pixel is nothing but a number, and that number is being shown with some gray color, a dark gray or a light gray color. So to see the individual pixel values, you have this tool here on your toolbar which says identify features. Okay, as soon as you select it and then click on any specific pixel, you will see a new box will pop up which says identify results. And here you see that the value of that pixel, I clicked on this bright pixel, the value of that pixel is 218. Now let me click on this dark pixel here. Now what do you think? Will the value will be lower than 218 or higher than 218? If you said lower, then you are right. Let me click here and you see that the value has now changed to 98. So the lower values are shown in dark colors and the higher values are shown in bright or white colors, whitish colors. So basically, since this is a byte data set, that means the values range from 0 to 255. So 0 is given black and 255 is given white, and the rest of the colors is like a grayscale palette, and all the different shades that you see are nothing but values from 0 to 255. Now let us randomly click on some pixels and see what values we get. So this forest area here, if I click on it, I get values like 99, 98, 105, and this urban area on inside Dehradun, I get 133, 114, 123, 140, and so on. So you see, in the band 2, that is green region of the electromagnetic spectrum, vegetation has a lower reflectance value. It reflects lesser energy, whereas the urban areas, they reflect slightly higher energy. Now, if band 4 is the infrared band, and infrared reflects more energy, then this vegetation patch here should appear brighter in band 4, in the NIR band. So let us turn this on and look at this feature here. So if I turn this on, you see that certain portions of this black patch have turned bright or white, not the rest of them. That means, although this area here doesn't have settlements or built up, not all of it is vegetation. Parts of it are vegetation, which appear bright, and parts of it are bare ground or fallow and things like that. So this kind of information can be extracted from different bands in satellite data sets. So it becomes important to visualize all the bands together. It becomes important to visualize all the bands together. So to do that, we will create what is known as the false color composite. We will create what is known as the false color composite. Now, false color composite is a generic term which is used whenever we merge 3 bands and create a false color composite, which is not the natural or true color. In natural or true color, the red band goes to the red color, the green band goes to the green color, the blue band goes to the blue color. That is why it is called the RGB image. But in a false color composite, you show the NIR band, that is band 4, with red color, the red band with blue color, and the green band with blue color. It may sound confusing, but you will get a hang of it as soon as you start doing these. So, okay, one more thing I wanted to tell you here is that when you want to see different pixel values across different bands, then also you can use this identify button. You can just click on any specific pixel, and in this identify results box, at the bottom you see an option which says tree. You can change that to table. Change the first option first, that is mode, to top down. That means all the values from all the layers from top to bottom, and view table will get displayed here. So as soon as you click on any pixel now, you are seeing 3 values are getting displayed. What are these 3 values? These are from band 4, band 3, and band 2. So whenever you click on any pixel, simultaneously you will have 3 different values appear in the identify result. How to get this? All you have to do is change 2 options. First, the mode to top down, and tree and view from tree, change it to table. So as soon as you do that and click on any pixel, you will see 3 different values from the 3 different bands will appear in this identify result box. Now let me close this box and let's now focus on how to create a false color composite. To create a false color composite, first step that we need to do is create what is known as a layer stack. So we will stack our 3 bands into a single file, into a single image. To do that, you need to go to this menu option, raster, click on miscellaneous, or bring your mouse down to miscellaneous, and then click on this option which says merge. So we are going to use this option called merge, which is there inside raster, miscellaneous, merge. As soon as you click on it, you will see a new box has come up. And this box asks you for some things. First thing that it asks is input layers. Which layers do you want to merge together? So I want to merge these 3 bands. Make sure you have the 3 bands added to QGIS. Click on this button, which just has 3 dots, which means it is the browse button. Click on the browse button. You will see that the 3 bands are listed here. Band 2, band 3, band 4. Now I told you we are going to create a false color composite where the NIR band, that is band 4, will go to red color. So to make sure that band 4 goes to red color, I need to make this at the topmost band or the first band. So what I'll do, again, same thing, just click and drag it to the top. Left click with your mouse and drag it to the top. So now you see the band 4 is the first band. Band 3 has to be the next band. So I will drag and drop it here. So now I have interchanged the order. The first is band 4, then band 3, and then band 2. Click on this button, select all, click on OK. Now this option is very important. You must make sure that this option is checked. By default, it is unchecked. You make sure that this box which says place each input file into a separate band has been checked. Okay, then it will place them as separate bands. If you don't check this option, it will not be able to merge these 3 into 3 different bands. The output data can be set to unsigned int 16 because the input data itself is unsigned int 16. And let me save this, the merged file. If you don't give an option, any value here, it will be saved into a temporary file. In Windows, they go into a temporary folder or the temp folder, which the data gets deleted once you close QGIS. So it is, if you want to retain the file, then you need to click on this browse button and say save to file. If you're doing some experimentation and you want a temporary file, you don't want to save it, you don't need to give any option here. Or if you want to actually save it, which I want to do, I will click on the save to file, go to my data folder and write a name, let's say FCC, and click on run. As soon as the run is complete, you would see the false color composite has already been added to QGIS map display. Close this box, click on the close button, and there you have a newly created false color composite added to your map display. Doesn't it look nice? Now, can you tell me what does the red color here indicate? The red color in the false color composite indicate? If you said vegetation, then that is right. The red color here indicates vegetation. See pink or light red colored small parcels or dots, they are agriculture farms. It is also interesting to see that a river which flows very close to Dehradun city appears in the same color as that of the built-up region. That is because of same material being used, they are of the same material, and it is very difficult to segregate using normal classification techniques that you will see at the end of the session. Okay, so now we have merged our three bands from grayscale. Now we have a colored image. Now let me show you how to enhance these images. Okay, so I'll just switch off the false color right now. We'll focus on band 4 for the time being, or any one of the grayscale bands. And you are seeing here some information, but if you zoom in, you have this thought that maybe we could enhance it. If we can make the brightness or contrast better, we should be able to see the features better. So to do that, the first thing you need to know is what is histogram, how to see a histogram. So a histogram is nothing but the frequency of the pixel values. So the pixel values I told you range from 0 to 255. Now, in how many pixels the 0 value is there, in how many pixels the 1 value is there, the 2 value is there, up to 255 will be shown like a graph, a bar chart. That is what is known as the histogram. And how do we see the histogram? Just make sure you have highlighted the layer that you want to see the histogram of, and go to the layer styling panel. In the layer styling panel, there are very small buttons. The first one which says symbology, the next one transparency, the third one says histogram. So you need to click on this and then click on this button which says compute histogram. There you go. So you see a nice bell curve. The minimum value is 0, the maximum value is 255, and you see you can use your mouse as a zoom. You can click and drag and zoom some area, and you can see that, let's say, the pixel value 120 occurs in about 200 odd pixels, whereas the value maybe 175 occurs in 1150 different pixels. So this is what a histogram looks like. And this display, what it is doing is setting the minimum value to 61. That is the value 61, which lies somewhere here in the histogram, has been set to 0 or black, and the value 364 somewhere here in the corner has been set to 55 or black. Now we can stretch the histogram. You may have learned of different image enhancement techniques. First one that we will learn is linear stretching. Okay, we will stretch the image and we will use what is known as the cumulative count cut. So you have a histogram. If you draw the cumulative distribution frequency, you will get a graph which looks like this. And we will take the first 2% off and the last 98% off threshold. And then we will stretch the histogram. And we will see the image will get enhanced. We will also see how the histogram differs or changes. So first, let's see how the image gets improved. You need to click on now from histogram, I have moved to the first tab, which is called symbology. Inside symbology, there is an option which says contrast enhancement. Make sure it is set to stretch to min max. Sometimes it goes to no enhancement. So it may turn black or you may not see any change. Best thing to do is select this option to stretch to min-max. Then there is a nice option which is collapsed by default. You need to expand that. Now you see several other options: user-defined, cumulative count cut, min-max, standard deviation, and so on. So by default, the min-max option has been selected. Now, as soon as I click on this radio button, which says cumulative count cut 2% to 98%, you will see that the visualization will change. So I'm going to click this now, and now you see the image appears brighter. Things which were not very visible in the previous image have now become quite understandable. These are the major roads in Dehradun city. These are different green patches. This is the center part, which is totally built up. So it is appearing very dark in the band 4, that is NIR region. And as you go away from Dehradun towards the hills, you see several places you have bright patches, which are vegetation, and some dark patches, which are other vegetation classes or shadow regions. So we changed the histogram, we changed the distribution of which the pixels are displayed. So now let us go back to the histogram and see what difference it has made. Oh, the histogram appears to be same. What happened? So we need to check or change another option. Click on this button here, which says preferences/actions, and select this option which says zoom to min-max. As soon as you do that and you switch and come back again, you see that the structure of the histogram has changed. Earlier it was like a bell curve. Now it is stretched. So the minimum value now is set to 113 and the maximum value is set to 224. So we have basically taken the histogram and linearly stretched it equally on both the directions. And we see that certain features have got enhanced. Similarly, you can try changing these options to 1%, 99%, or 3%, 97%, or unbalanced cuts. Or you can also use these options, which is mean plus minus standard deviation, 2%, 1%, 3%, and so on, and see whether the features that you are trying to detect from your satellite images get enhanced or subdued. Okay, so these are different ways of how you can enhance the contrast in your images to get better representation of features on the ground. So till now we have seen how to add images, how to create a false color composite, and how to enhance the appearance of single band images. The next thing that we will do is known as spatial enhancement. In spatial enhancement, what we will do is we will be creating new files and we will be running some filters on these existing images. Now, what are filters? These are spatial filters. These are kernels, 3x3, 5x5, 9x9, odd numbered kernels or square boxes that are run over the image row-wise, and some mathematical operation is applied. So I think some theory lessons you must have undergone on filters. So there are two types of filters. Do you know which are they? Yes, that's right. Low pass filters and high pass filters. Now, low pass filters are also called smoothing filters, whereas high pass filters are called sharpening filters. So we will apply both of them on the image and see what differences does it make. Okay. So let's take this itself, band 4, and see how we can apply low pass and high pass filters. Now, to apply low pass and high pass filters, we will be using another software which is plugged inside QGIS. So you don't need to open anything else. Inside QGIS itself, you have two other softwares, the functions from two other softwares available. One is called Saga. Saga itself is a very popular GIS software, very advanced, which is developed by several universities in Europe. And it is a very powerful software if you're looking for some advanced algorithms. You must explore this software called Saga. It gets pre-installed along with QGIS. So again, you don't need to install anything. If you go to your start menu inside QGIS, you will see that Saga has also been set up. But we are not going to demonstrate Saga. Instead, the functions from Saga have been brought inside QGIS. Okay, so we will use some Saga tools to run our spatial filters. So where are these tools? So you need to open the processing toolbox. Again, if you don't see your processing toolbox, you need to go to View, Panels, and make sure that this box is checked, which says Processing Toolbox Panel. As soon as this panel opens, you need to go to the last option. In this software, it is showing as last. I had a different version where this was second last or third last. So just look for Saga in this list. Also, if you are seeing this toolbox as something like this floating around, you can dock it here so that it gets fixed in one place and does not change its position when you are doing certain things here. Okay, so in processing toolbox, you need to locate this option which says Saga, expand it. Inside this, there is another option which says raster filter. Inside this, there is an option which says simple filter. Okay. Obviously, it's very difficult to remember this whole path inside Saga, raster filter, simple filter. So what they have done is they have given a very simple search box here. You can just simply type, and as soon as you start typing, it will start searching. So as soon as I typed S, it is giving all the tools which has the name S in it. So I want simple filter. So I typed simple, and all the tools which have the name simple in it have come up. I am looking for this option, Saga, raster filter, simple filter. Just double click on it and you will see a new box to apply the simple filter has come up. So we are going to apply the simple filter on this band 4 image. In Saga, they refer to the rasters as grid. Okay, they refer to rasters as grid. So nothing to worry about. This grid is nothing but raster. So you can select any of the rasters which are open here. I'll stick to band 4. Then there are two search modes, circle and square. So your kernel can be circular or can be squarish. Generally, we'll take square because it's easier to calculate the values. Then you have 3 different filters, smoothen, sharpen, and edge. So I'll show you what are the outputs with smooth and sharp. I want you guys to try with circle and different combinations and see what difference it makes. So let me take smooth first. I'm going to show you a low pass filter that is called the smoothing filter. And then we'll set a radius. Now what is radius? Radius is basically the kernel size. So if I set radius to 1, that means we are talking about a 3 by 3 kernel. If I set radius to 2, that means we are talking about a 5 by 5 kernel. And if I set radius to 3, we're talking about a 7 by 7 kernel, and so on. The bigger the radius, the more or enhanced is the effect. So if I use a smoothing filter with radius 1 and a smoothing filter with a radius 5, the one with the 5 will appear to be more smoothed. Okay, so let me take 3 and just to enhance the appearance. And since I don't need to save the output anywhere, this is just a experimental output, I'll not change where the filtered grid, that is the resulting output, will be saved. It will go into a temporary folder and which will get automatically deleted when I close QGIS. So let me click on run. It will take some time. It will first convert the file to a Saga format called SDAT. Then it applies the filter and then produces the result. So this may take few seconds and it will give you the smoothened output. Okay, let me save it somewhere. Let's call it smooth. Run. Okay, so we got a Windows prompt saying the simple filter task is complete. Let me close this, and now the smooth output is automatically added. Now let me just zoom to an area, and by now you have already understood what the output, how the output has changed. Okay, so let me set. Now you are also seeing this difference because the stretching values, the contrast enhancement is different. Now to set both of them, both the layers to the same contrast enhancement, this is what you need to do. You need to copy the style from this layer and paste it on this layer. Okay, so how do we copy the style? You need to right click on the layer name. The second last option says styles. Copy the style, go to the other layer, right click, styles, paste style. Okay, so what we are basically doing, we are copying the contrast enhancement options from one layer to the other layer. So paste style here, and now if I turn it on, you see now both of them are at the same stretch, 113 to 224, 113 to 224. And now you will be able to appreciate how the output looks blurred. Okay, I'm just turning the output off and on so you can see the changes in the two outputs. So you can see how the output has the smoothened effect. So this is what the smoothing filter does. Now let us try to do the or same process. You just need to change from smooth to sharpened, and I want all of you to try how sharpen works on the image and tell me what is the differences that you observe. Okay, the next thing that we are going to do is known as band ratioing. What is band ratioing? Several times the features that we are trying to interpret from the data is not decipherable in a single band. We need to create an index using 2 or even more bands. So we can use things like simple division of two bands, or creating what is known as normalized difference of two bands, or there have been several studies, different formulas to enhance a specific thing. For example, index called vegetation index, or VI, enhances the vegetation. Some researchers found a better index. They called it NDVI, or normalized difference vegetation index. Some researchers use the same formula but different bands to enhance, let's say, water. They called it normalized difference water index. Some researchers found a soil indexed normalized difference soil index or snow index, and so on. So there are several indexes. These are basically mathematical operations on different raster bands. Now, how do we do that mathematical operation? So this time we will not use the processing toolbox, rather an inbuilt tool of QGIS, which is called the raster calculator. The raster calculator allows you to do arithmetic, trigonometric, and several other mathematical operators in QGIS on raster data. So let's click on this raster calculator. Here you will see all your data is already listed. So these are single band images. FCC is a 3-band image. So it says FCC at 1, at 2, at 3, and then a smoothened image. So I'm interested only in band 4 and band 3 right now. That is my infrared and red band. And let me see how I can create a NDVI image. A lot of people talk about NDVI. How do we create an NDVI? So the formula is pretty simple. The formula goes like this: NIR minus red divided by NIR plus red. If I talk in terms of band numbers, it is basically band 4 minus band 3, whole thing divided by band 4 plus band 3. So how do we write this? Simple. With your keyboard, you can type brackets, or you can click on these open and close brackets. So let me open this bracket, double click on band 4 minus band 3, close the bracket, divide, open bracket again, band 4 plus band 3, and close brackets. So right now we have written a formula. It may appear daunting, but it is actually a very simple formula. A minus B by A plus B. That's all. Now let me save this output to my data folder. Let's call it NDVI. And let's click on OK. So you see it has created an image called NDVI, which has a lot of bright areas and a lot of dark areas. And NDVI basically tells you about the greenness of an area. Now, this is a single band image, but it would be better if I could show the higher values not with white, but with green, and the lower values with not black, but maybe brown, to show that the higher values are greener and the lower values do not have vegetation. To do that, we will use what is known as a pseudo color. Okay, so you need to go to the layer styling, make sure NDVI is clicked on, that it is highlighted. Go to layer styling. Then in layer styling, in the first tab, which is symbology, click on this drop down, go to single band pseudo color, and click on classify. Wow. Now the NDVI makes more sense. These areas, there are dense vegetation, probably forest. Then the orange blue colors show lesser vegetation, probably fallow or croplands. and the red color shows no vegetation. That means these are built up, and this linear feature here is a dry river bed. So using the NDVI also, you can find out a lot of information about your study area by creating these different indices. If you want to find water bodies, then you would create what is known as NDWI. That requires a different set of bands, but the formula is pretty similar, A minus B by A plus B. Okay. The next, now we go to another image processing technique called principal component analysis. Now, do you know what principal component analysis, abbreviated as PCA, does? So PCA is a technique for dimensionality reduction. Very big words. What is dimensionality reduction? These bands that the satellite or the sensor is capturing data in, they have a lot of dependency among each other. A lot of the bands may appear very similar to you because there is interdependency between them. Can we find out how much correlation is there between these bands? Can we extract all the useful information in minimum set of bands? That is the idea behind doing PCA. So let us first find out how to do correlation, or how to find out the correlation among the bands. Okay. To do that, what I will do is I will save this project and I will create a new project. Okay. So I have clicked on this floppy disk, which says save project. And then I am clicking on this white page here, which says new project. So all my layers will get removed, but nothing to worry about. We have all the things stored in my project. For the PCA part, what I want to do is I want to add all the 4 bands. Till now, we were using only 3 bands, 2, 3, 4. Now let me add all the 4 bands, 2, 3, 4, and 5. Drag, drop. Very simple. So right now I have 4 bands in QGIS. I have removed everything else. And I want to find out what is the correlation between these bands. How much of the information in one band is repeated in the other band. Okay. So to do that, we will be using a tool which is not in QGIS, not in Saga, but in another very powerful GIS tool, RSM GIS tool called GRASS. This GRASS is also pre-installed with your QGIS. If you go to your start menu and go to QGIS, the first thing that you will see, since it alphabetically, will be GRASS GIS. GRASS GIS is one of the oldest and most powerful GIS softwares. And some of the functionality from GRASS has been captured into or been shared inside QGIS. So you don't need to open GRASS separately. You can directly use the GRASS functionalities inside QGIS. The GRASS tools have been categorized as imagery, miscellaneous, raster, and so on. So in this, we will go to raster, GRASS raster, and there is a tool which says r.covar, r.covar, C-O-V-A-R, which stands for covariance or correlation. Just double click on this tool, select all the input layers. The ordering does not matter. Just say select all, click on OK. And that's it. Click on run, nothing else. Just select the files and click on run. So what it is doing with each band, it is trying to find out, okay, I need to save the output files because I do not have admin rights on this system. I need to save the file to my directory. Let's call it report in my D drive data. And let's run it again. That's it. It says the HTML output has been generated. Close this box. At the bottom, you see a result viewer. At the bottom, there is a hyperlink, a link which you can click on. Click on that. A browser will open with a table like this. Now, how many rows does it have? It has, if you leave out the first one, it has 1, 2, 3, and 4 rows. And how many columns does it have? That's right, it has 4 columns. That is 1, 2, 3, and 4. So basically, I have 4 bands, and it has generated a 4 by 4 matrix. If you look at the diagonal elements, you will see that all of them are 1. That means the correlation of the first band with itself is 100%. Correlation of second band with itself is 100%. Correlation of third band with itself, and so on. So this is basically band 1. The first row is band 1. The first column is band 1. Second row is band 2. Second column is band 2, and so on. So what this number tells you is 0.976 is that the correlation between band 1 and band 2 is 97%. The information that is there in band 1 is roughly repeated about 97% times in band 2. Whereas band 1 and band 3 are correlated only about 50%. Band 1 and band 4 is correlated about 75%. So you see that there is a lot of redundancy. If you are going to use some automated ways to do classification, you are unnecessarily putting in junk data. You are putting repetitive data. We want unique data to be entered. To do that, we need to reduce the number of dimensions. We need to reduce the number of bands. And there are different dimensionality reduction techniques. PCA is one of the most popular ones. So we generated a correlation covariance matrix. The next thing that we need to do is run the PCA. This tool is inside GRASS. Imagery I.PCA. I.PCA. So you are seeing there are so many other tools, HIS, pan sharpening, segmentation, SMAP, tacit cap, so many different algorithms are there. There is a suite of image processing capabilities in GRASS, Saga, and QGIS. In this short 1.5 hour demonstration, I'm just showing you, you could say, the tip of the iceberg. So let's start this tool, I.PCA. Let's, the first option says name of 2 or more input raster maps. You must give at least 2. Right now we are giving all 4. Click on select all, click on OK. And give the output directory, that's all. So save directory and click on select folder. I'll save it here itself in my D drive in data and click on run. A small thing to note here is that these Saga and GRASS tools, they are not very friendly with paths, that is folder structure having spaces in them. Okay, so if you write a folder which says QGIS space image, space processing, space data, then the tool may not run. So I've come across those problems. That is why I'm suggesting that whenever you write a folder name, try to avoid spaces in them. So if you have something like my project, don't give my space project. Instead, you give my hyphen project, or you use camel case, M capital, P capital, or you use an underscore and things like that. Okay, so that was very fast. It generated the PCA. Now let's close this and let's add one of the bands. So if you see if you see the data folder, you will see a lot of files have been created. So the same number of input bands will be created in the output, 1, 2, 3, and 4. The names are a little obscure. It says output followed by a big number. Then at the end, it says 1, 2, 3, and 4. So 1 is the first principal component, 2 is the second principal component, 3 is the third, and 4 is the fourth. The most or the maximum information is there in the first principal component, almost 98, 99%, followed by 1 or 2% in band 2, and very less information in decimal numbers, less than 1 in band 3 onwards. So let me add the first band to QGIS, and let's see the output. Something is not right. So, but one thing that I can show you is that if none of the layers are displaying. Okay, then I'll have to add everything again. Okay. Fortunately, I have another session ready. So let me add the outputs. So this is the output of the PCA exercise. And you see that you will see if you do the correlation covariance again, that this first band has roughly 97, 98% of all the information that is there in all the 4 bands. Okay. So we are reducing the dimensionality. We are concentrating the information in a single band. And if you create the RGB using the first 3 principal components, you would get a lot of information about the features on ground. The last thing that I want to show today is unsupervised classification. So basically, you are going to do a lot of classification to create what are known as land use land cover maps. You will be downloading either list 3, list 4, Sentinel, Landsat, these different data sets, and you will add it to GIS or tool and classify it. There are 2 primary classification techniques. One is called unsupervised or clustering, and the second one is called supervised. So in supervised classification, you need training samples, which should ideally be collected from the ground. So you should go on the ground where you are doing land use land classification and collect GPS locations of the data that you want to of the classes that you want. So for example, you want forest, or you want a specific type of forest, deciduous, evergreen. If you want crops, if you want specific type of crops, wheat, rice, corn, etc., you have to go to field and collect GPS locations, points of those where the features are existing, and then come back, add the same date data, and then use a supervised classification technique. So right now I don't have those points. So I'll use a simpler method, which is called the unsupervised classification techniques. There are several unsupervised classification techniques, and one of the most common one is called k-means clustering. So how to do k-means clustering? That is inbuilt in Saga. You go to Saga, image analysis, k-means clustering for grids, select your input bands. There are different methods available. I'll use the default method. Normally, you must create more clusters, something like 20. If you are creating 5 classes, then you should have at least 4 times. That is, if you're creating 5 classes, you should have 20 clusters. So right now, for simplicity and saving the time, I'll just keep as 5. Number of iterations will improve the quality of the results. So you make it as much as you want. I'm putting it as 20. And I am going to save this as unsupervised. And let me run this and let us have a look at the output. So what we are doing is we are taking the 4 bands, plotting it on a 4-dimensional space, and the program itself tries to calculate 5 different clusters in this 4-dimensional space, which can be separated and made as 4 or 5 different classes. There are different techniques to do it. There are newer advanced things like AI, machine learning, SVM, random forest, this, that. So several techniques, but the basic technique is k-means. You should know how these classes are separated, something called separability analysis, and what is the distance between them in n-dimensional space, and so on. So right now, this algorithm has run. It has created 4 clusters. Let me go to layer styling and give it 4 values. And these are not the right colors, but basically what I want to show you is using very simple steps, you can do unsupervised classification, supervised classification, and higher order classification using Saga, GRASS, and QGIS. So that is all I want to share for today. Again, all the data and the handout for today's exercise is available at this link, bit.ly/image-processing-QGIS. And this is my email ID in case you want to get in touch later. Thank you very much. We will take some question and answers in about 5 minutes. and I thank my team for filtering them. Okay, we'll take the first question. The first question is from Priyadarshini. She asks, why red color is vegetation? Very good question. So this has a more biological answer than geographic answer. So the thing is, let me add the FCC first. So the thing is, biologically, human eyes, the eyes that you and I have, are more sensitive to the red color. The human eyes are more sensitive to the red color. And we can easily differentiate, if you look at this image which is displayed right now, you can easily differentiate the difference between the red color here, which is at the outskirts of Dehradun city, as compared to the red color on the hills. These are more dark, these are more light. And we can even differentiate, if I zoom into this area, in these different shades of red. So this is the FRI campus, the Forest Research Institute. And here within this campus itself, you can see so many different shades of red. This is an experimental forest that they have, which is dense, the dark green. Then they have another set of forests, which is light green. This is the main path which enters, which is road and partly with large lawns on them. So that is why it appears with this light red. So the answer to your question is vegetation is purposefully shown in red because our eyes can capture the differences more easily. But false color composites is a generic word. False color composite is a generic word. Now, for example, if you want to detect fires, nowadays forest fire is a very important thing. There are so many forests burning across the globe. So, so what if I wanted to identify fires? So some bands which are in the end of the electromagnetic spectrum, they are more sensitive to heat. So if we create a false color composite using those bands, we can actually see the fires as orange or white pixels. Okay, so that requires different set of bands. I suggest that you go through something, just search for Landsat band combinations. There are different, Landsat has so many bands, and they can be combined in different ways to emphasize. So this, if you take Landsat 432, you get natural color or true color. If you take 543, you get color infrared. Here vegetation appears red. If you take 764, you get shortwave infrared. These are used for urban and soil identification, then agriculture, geology, bathymetry. So different applications use different band combinations. Moisture index, you can arrange some bands in an order where you can identify soil moisture. So arranging different bands in different colors highlights certain features. Okay, showing vegetation in red is just one use case of creating a false color composite. Mandeep Singh has a very interesting question. He asks, can we use the same techniques in ArcGIS Pro? So this demo is on QGIS. QGIS is a very powerful, very popular open source GIS software, which does not cost you a penny. You don't have to spend a single cent, rupee, dollar from your pocket, whereas ArcGIS Pro requires you to spend ranging from, I don't want to get into economics, but requires a lot of money to buy and use, except, of course, if you want to resort to illegal measures. But yeah, if you have a lot of money, you go for ArcGIS Pro. Yes, you can do the same things in ArcGIS Pro. If you don't have money and yet you want to do all this, QGIS is there for free. What is the next question Mandeep asks is, what is the difference between ILWIS and QGIS? They are both GIS, remote sensing GIS softwares. ILWIS has a history where it started in ITC, the Netherlands, and then it was closed source. You had to purchase it. And then in somewhere in 2008, they open sourced it. Now an organization called 52 Degree North is developing and promoting it. So yeah, it also does quite a lot of things which you can do in QGIS, which I showed you, and more. But QGIS is very popular. QGIS has a very wide user base. If you get into trouble or if you get stuck with something in QGIS, there are more people to help you out on the internet as compared to ILWIS. The next question is by Umar. He asks, how to integrate Saga and QGIS and work simultaneously? So you don't need to... So Saga is a very powerful software in itself. The primary aim of Saga was to make tools which could be used in command line mode or API mode and so on. The second, this is from their documentation. The second objective of making Saga was to make a GUI. So although it has a very powerful GUI, has a very powerful API, but the same tools in Saga have been borrowed, have been shared inside QGIS. So I agree, not all of them, all the capabilities of Saga are inside QGIS, but a lot of it is already there. So you don't need to explicitly work on Saga. You could simply work on QGIS and use Saga tools and worry nothing about it. So whatever products are being created, for example, you saw some SDAT files are being created. They are all compatible in QGIS. So one thing that I forgot to show you is that QGIS supports all known raster formats. So if you have a GeoTIFF file or a ADAS Imagine file or a gridded binary file, NetCDF, HDF, ILWIS file, Saga file, any other obscure file format, it will open in QGIS. So the question of interoperability, if I work with ArcGIS, if I work with ILWIS, if I work with Saga, can I work with QGIS again? Yes. And all the outputs from QGIS will also open in all these different softwares. So QGIS is a highly interoperable, open source, free of cost software. Okay, so the next question is from, the next question is from, so many windows. How do you do spatial temporal analysis on remote sensing images using QGIS? So say spatial temporal is a very generic term. There are many algorithms to do spatial temporal analysis. Primarily what you want to do is do change detection, things like change detection or things like rate of change and stuff like that. So GRASS has a wide range of spatiotemporal algorithms. Some of them are borrowed inside QGIS. You could use QGIS to do them, or you could directly use GRASS to use it. If you know a little bit of programming, you can write your own algorithms with Python inside QGIS. So QGIS also has a Python programming API called PyQGIS. You can explore that also. Can we apply NDVI? The next question is, can we apply NDVI on a specific part of the map? Yes, you can do what is known as clipping a map. You can clip out an area and then apply QGI, NDVI or any other operation on it. Kansha asks where to get the band to add QGIS. Very good question. So if you are in India, then a lot of data is given for free by ISRO on this website called Bhuvan. Bhuvan is ISRO's geo platform. From here, just search on Google Bhuvan NRSC or Bhuvan ISRO, and here you will find a link which says Open Data Archive. You can go here. You need to create a login ID, so just like an email. And then you can go explore these different products which are available. The example that I showed was using this list 3 data for the Dehradun region. So I go here near Dehradun. Or if you don't know where your location is on the map, just search on this search bar and click on tiles. Click the tiles you are interested in, stop, click on next, and you will see that several data starting from 2008 up to 2019 is available for free on this platform. Okay, so this is where you get the data, Akansha. Go to this website, download the data, download QGIS, and you can become, or you can do GIS on yourself, on your laptop without any money. Is there a same procedure for NDVI and NDWI? Yes, except that the bands are different. In NDVI, you require the NIR and the near infrared and the red bands, whereas NDVI formula is NIR, that is near infrared minus red by NIR plus red, whereas NDWI requires, I think, the green and the NIR band, green minus NIR divided by green plus NIR. So you have to find out which band is green, which band is NIR, and write the same formula. Procedure is the same, the formula is the different. Again, heads up, NDWI, there are some literatures. There are 2 very important papers. One is, I think, by Cow, the other one is by McFeeters. They have proposed different formula for NDWI. So those who are interested in doing a little bit more research can find out what are these 2 papers and what are those formula. What is the next question is by Suraj. She asks, what is the difference between Saga and QGIS? Is Saga more better than, QGIS more better than Saga? There are hundreds of different softwares in open source domain also. And some of them are very specialized. For example, LAST tools is made only for LiDAR data processing. There are other tools which do specific tasks only. A general purpose remote sensing GIS software which is very popular is QGIS. Saga is also a popular software, but it is primarily meant for those who want to do advanced algorithmic stuff. If you want to add data, visualize data, make maps, do basic processing, QGIS is the best. If you want to do advanced algorithms, machine learning, and all that, then you must learn GRASS, Saga, as well as QGIS. I think I'll take these questions only for today. I have shared my contact details If you have any further questions, please feel free to contact me. Thank you very much.